All right, so I'm teaching you how to predict the shapes and the bond angles of molecules using VSEPR theory. VSEPR theory stands for valence shell electron pair repulsion. And what's happening is you will have bonded atoms and lone pairs of electrons on a central atom that will repel each other because they contain electrons that are negatively charged, and we get a distinct shape. And we can predict that shape when I teach you the MXE method. If you take a look in the module for this chapter, there is a document that has all of these designations on it that I'm going to be outlining first before I do some examples. So if you're looking at a molecule, M is what we are going to assign for the central atom or the atom around which we want to determine the shape. X is what I'm going to assign bonded atoms or groups of atoms that are coming off of the central atom M. Okay? And then if I'm looking at a molecule and it has lone pair electrons on the central atom, then we will designate that with an E. And the arrangement of M's, X's, and E's will tell us the shape. Okay? So if we're looking first at carbon dioxide is CO2. It looks like this. I'm going to put an M on my central atom, which is my carbon. I have two groups bonded. It doesn't matter if these are single bonds, double bonds, or triple bonds. I have two groups bonded to the central atom, and those are my X's. I don't have any lone pairs of electrons on my central atom, so I don't have any E's. So my designation here is MX2. When your designation is MX2, your shape or your geometry is going to be linear. Now, they will sometimes refer to the geometries or the shape as a base geometry and then a molecular geometry. Sometimes the base geometry is called the electron domain geometry. We really just focus on the actual molecular geometry. So just so you know, the molecular or actual geometry, which would mean the actual shape, is going to be linear. And the bond angle is going to be 180 degrees. What that means is the bond angle here is 180 degrees. So it's a straight line. Okay? Now, the next one is going to be MX3. So if I have something like BCl3, this is the Lewis structure for BCl3. And I assign an M to my central atom, and then I have three groups bonded to that central atom. So that means I have three X's. I don't have any E's, which are my lone pairs of electrons. So my designation here is MX3. The designation is not the shape. We use that to help us get the shape, okay? So anytime it's MX3, your molecular geometry is going to be trigonal planar. And think of it as this is in the plane of the board, and these are repelling each other equally. So if this is 360 degrees and you divide it by 3, you're going to end up getting 120 degrees for your bond angle. So between here and here, 120 degrees. Okay? Now the next one is going to be MX2E. So if I'm looking at something like this, okay, I've got my central atom, M. I've got two bonded groups coming off of the central atom. I have one here and one here. I have a lone pair of electrons on the central atom, so that is my E. My designation is MX2E. Anytime that's the designation, what that means is you're going to have a bent shape. And the reason you're going to have a bent shape is because this lone pair of electrons here on the nitrogen, think of it as this huge negatively charged cloud that's taking up more space. than if I had an oxygen bonded off the top of the nitrogen. And it pushes things away from it. It repels things. So you're going to have the oxygens that are bonded to the nitrogen pushed away by that lone pair of electrons. And if I cover it up, do you see I have this bent shape? Okay? And then your bond angle here, typically when you have three things coming off of the central atom, it's 120 degrees. But since you have a lone pair of electrons present, the lone pair of electrons is going to change your bond angle by about 2 degrees. It'll be about 2 degrees less than what you would expect it to be. So you have to put a less than in front of it due to the presence of an E, which is a lone pair of electrons on the central atom. Okay? Okay, now let's go on to the ammonium ion, which is NH4 plus 1. So NH4 plus 1 looks like this. Your central atom is nitrogen. You have 4 groups bonded to it. I don't have any lone pairs of electrons on the nitrogen, so I have no E's present. MX4 is a designation. Remember, we use that to get the shape. And tetrahedral is the shape, and your bond angle is 109.5. So between here and here, it's 109.5 degrees. Okay? Now, if we're looking at PF3, looks like this. I have my central atom M. I have 3 bonded groups. I have 1 lone pair of electrons. So this is MX3E for my designation. Anytime it's MX3E for your designation, that means that trigonal pyramidal is going to be your shape. Now, how is it that we get this trigonal pyramidal shape? Well, the lone pair of electrons that is on the phosphorus here, remember that lone pairs of electrons take up a lot of space. So this huge negative charge that's pushing away the fluorines. So what happens is the fluorine being pushed away create this triangular base. And then think of this as being the top of a pyramid. That's how you get your trigonal pyramidal shape, okay? Now, when I have 4 things on a central atom, generally speaking, my bond angle is 109.5. But since I have a lone pair of electrons present and it pushes the bonded groups away more, that means that my bond angle here is going to be less than 109.5. And that is due to the presence of the E, or the lone pair of electrons. We have one more. Let's look at water. When you're looking at water, you have your central atom, M. We have 2 bonded groups, those are my X's, and I have 2 lone pairs of electrons, which are my E's. My designation is MX2E2. Now, why is it that gives me a bent shape? That's because I have 2 lone pairs of electrons on the oxygen, which you know take up a lot more space, and they are pushing away the bonded groups more than if that was another hydrogen coming off of the oxygen. So since these are pushing them away, if you cover up the lone pairs, you will see I have this bent shape in the water molecule. And then the bond angle here has to be less than 109.5 because I have the lone pairs of electrons present.